Today we will continue our discussion on chapter 1 related to energy classification and overview of energy conversion, with looking at the second part, which is a brief overview of the energy conversion process. Now, when we talk about the energy conversion, basically we're talking about, as the name suggests, we're talking about conversion of energy from one form to another, or conversion of the energy to more useful form, right? And when we talk about any conversion, energy conversion that happens, well, from first law of thermodynamics, we know that energy can certainly change from one form to another, but the total amount of energy will remain constant. But the second law tells us that the amount of useful energy that you may get is usually or is always smaller than the energy input that you have, right? So, but for now, let's talk about the conservation of energy principle, and let's write everything based on that. Okay, so when you talk about any energy input, right, to an energy conversion device, the device converts it into a more favorable energy output, something that you can use. Okay, and from first law, we have energy input is equal to energy output, which is basically written up here. But we know from second law that the useful energy output is always going to be less than the energy input, right? And so this is a list of different typical energy conversion devices along with their energy inputs and the useful energy output. The useful energy output is ultimately what we need, and which is why we purchase this particular device, right? And the efficiency tells us how efficiently it's converting the energy input or input energy into the useful energy that we want. Okay. Now, in terms of measuring energy, there are multiple ways of measuring it, right? And as we discussed in the previous class about the classification in terms of primary energy, the primary energy is absolutely the one that we start off with. So it could be something like coal, wood, oil, or whatever, right? It's something that's stored in nature or it's available in nature, and then you convert that into a secondary form, which is something more usable, right? But it's not something that you directly use eventually, or that's not the end use in right? So basically, if you're talking about the use of a coal to light to power a light bulb, so then well, you use coal as a fuel in a power plant to generate electricity. Coal is a primary energy, and electricity is a secondary energy. And of course, in this conversion from primary to secondary energy, there will be losses. Okay, and these losses are usually on the larger side. Now, when you're at the secondary energy, this is still not the energy we directly use. This is at a power plant. So this needs to be transported and delivered to the home, right? And so there are some losses in the transmission and distribution, which are usually on the smaller side, very small, but not negligible. Okay. And once it's delivered to your home, of course, we don't use electricity directly, but we use electricity to power a lot of energy conversion devices, one of which is a light bulb. If you want to generate light, if that's all you care about, right? So if you want to get light, then you need to have a light bulb, which is your energy conversion device, and its energy input is the electricity. And what you eventually get is useful energy. This is ultimately the desired output. And to get the light from a light bulb in your home, you have to go through the energy goes through all of these different energy conversion processes with losses at each stage. Now, when we talk about the energy conversion itself, it can be divided into two major categories. It can be classified as direct conversion and indirect conversion, right? Depending on the kind of device that you have. Now, there are a lot of direct conversion there are a lot of devices which can do direct conversion, such as photovoltaic or PV cells, which convert the electromagnetic radiation of the sun directly into electrical energy, right? Other things such as batteries, thermoelectric coolers, piezoelectric chips, all of these, what they do is they convert uh, the energy in a form which is available, let's say, which could be primary, directly into the desired energy source, right? And so, such as batteries from chemical to electrical, TECs from thermal to electrical, and piezoelectric from mechanical to electrical, right? Now, these are, of course, very interesting devices, very useful devices, but these are usually the minority. The majority of the devices that we have around us uh, are what are called as indirect energy conversion devices, or they have a multi-step conversion process. Okay, so let's take, for example, a diesel powered bus or a diesel powered truck, right? So what happens in that is the chemical energy in the fuel gets converted to thermal energy because of combustion. Now this thermal energy then drives the piston up and down. It causes the motion of the piston, and then the piston itself does not move the car. You need to have a transmission which converts this mechanical motion into another mechanical movement, which is the rotation of your tires, right? Eventually, through the transmission. So you have multiple energy conversion processes with loss at each stage, which allows you to ultimately uh, accomplish your desired task. Now, just because we have multi-step conversion process does not necessarily mean that the efficiency is going to be small for this, right? It could be better, right, than direct conversion. It just depends on the efficiency and depends on the process that you're talking about. Another example could be something like a steam turbine, right? It makes use of chemical, nuclear, solar, geothermal, any of the energy sources, converts that into thermal energy by heating up water into steam. And once you have steam, the steam drives the turbine, which is mechanical energy. And this energy is converted to electrical energy with the help of a generator. Now, you do something similar in a gas turbine, although we don't have a phase change. In a gas turbine, you simply convert the chemical or solar energy to produce thermal energy, hot gases essentially, which then expand within a turbine and rotate it. And then eventually, with the help of a generator, we convert that into electrical energy. Now, when you look at the energy conversion process for a steam turbine or a gas turbine, the efficiencies range somewhere between 35 to 60%. 60%, of course, for a combined cycle power plant, right? But if you're talking about the same thing, if you're looking at converting solar energy or into electrical energy using a photovoltaic cell, well, uh, for such a conversion process, the the efficiencies can be as low as 15%, right? Now, if you instead of using direct energy conversion, if you do something like solar to thermal and thermal to mechanical with multi-step conversion process, you may also eventually reach somewhere around 15 to 20%. So just because we are having multi-step conversion process does not necessarily mean that the efficiency is going to be on the lower side. Okay, so that's something to know. And of course, these are what we have in the majority of the processes around us. Now, when we talk about the quality of energy conversion, we use efficiency to define or describe the quality of energy conversion. And obviously, you want the efficiency to be as high as possible. And efficiency by then is sort of is defined as the ratio of the desired output or the ultimate useful output that you need divided by the required input. Okay, and so you would want to pick a device which is as efficient as possible simply because you would want to minimize input, right? And get the same exact output. So now when we talk about the efficiency, well, as we know from second law, uh, not all input energy is converted into the desired form. Some of it is converted into undesired forms, such as low-grade heat or something, which is why the efficiency of energy conversion in almost all devices is less than one, right? For all heat engines, it's surely less than one. Okay, and most of the times the undesired energy that you get is low-grade thermal energy, and you really cannot make use of it for anything else. Now, let's take an example of a light bulb. Okay, so when you're looking at a light bulb, the whole purpose of purchasing a light bulb is because you want light energy. That's all you care about, right? And now, in terms of its efficiency, if you're talking about an incandescent light bulb like the one we have on the left, well, the useful output is the light energy, which is 10 joules. But the required input is the electrical energy, which in this case is 100 joules. So its efficiency is 10%, right? Not very efficient. On the other hand, if you move to an LED bulb like the one shown here, again, the desired output is light energy, which is 75 joules here, and the required input is electrical energy, which is 100 joules. So this one has an efficiency of 75%. So obviously, between the two, you would want to pick up a device which has higher energy efficiency, right? High energy efficiency always is a winner when the input is exactly the same, which is electrical energy for both. Okay. Now I just want to show you through a very simple example the huge effect or the huge positive effect of picking more energy efficient devices and how they can drastically reduce the energy consumption, the primary energy consumption, and thereby the carbon emissions themselves. Right. So let's consider the entire scenario of lighting a bulb or to get to get light energy and the entire process it has to go through. Now you want to ultimately light up a bulb, right? You want to get some light, you want to light up your room. That's all you want to do. But for doing this, we need electrical energy, right? And we let's in Saudi Arabia, we produce electricity mainly through oil and gas, right? And that's our primary energy. Let's say you start with 100 joules of primary energy or 100 units of primary energy. In a typical power plant, the typical power plant has an efficiency of 35%, right? I'm talking about um, steam power plant usually. And so at, when you're looking at efficiency of 35%, then you can say that out of the 100 units available, only 35 units get converted to electricity. The rest is all rejected to the atmosphere as waste heat. Okay. Now, that's the power generation step. Next step, well, this is electricity generated, but it's not in your home. It's somewhere in a faraway power plant. You have to take care about transmission and then ultimately distribution through a transformer. So once you transmit it through the grid lines to to the area, and then you distribute it further through transformers, there are going to be some losses, 1.5% in the transmission stage, 2%, about 2% in the distribution stage, and then ultimately it reaches the socket of your or the bulb socket where it needs to power the bulb, right? And within the wiring, let's say the losses are 0.5%. So starting with 100 units of energy, the the major loss happened within the power plant. It became 35 units. And then there were some transmission, distribution, and wiring losses, which made the energy 31.5 units, right? So starting with 100, you are at 31.5 units at the time when you want to light up the bulb. Okay. Sorry, 31 units at the time when you want to light up the bulb. Now, we know that the efficiency of incandescent bulb is 10%. So out of this 31%, only 10% is used, which means that the light energy you get is roughly 3 units, right? The rest 28 is just wasted as heat. Okay. So in this scenario, it makes sense to sort of compare how would the energy requirements for an LED bulb change when you replace this incandescent bulb with an LED bulb. So now, you know, um, as we have seen in the previous case with an incandescent bulb, the amount of light energy you get in your room is just, let's say, 3 joules, right? And this is ultimately what you wanted. But for this to happen, we needed 100 joules of primary energy, right? Which is crude oil, let's say, equivalent amount of crude oil. Now, because an LED bulb has a much higher efficiency, if the amount of energy reaching the home electrical energy was 31 joules, then the LED bulb would convert 23 joules of it to light energy, right? Because its efficiency is 75%. Okay. Now we really do not need 23 joules. What we need is 3 joules. So the question is, for 3 joules of light energy, how much electrical energy would the LED bulb require? Well, if you do the math, what you will find out is that LED bulb requires only 13 joules of energy, right? Of primary energy, that is. So just by changing a bulb from an incandescent bulb to an LED bulb, you're reducing energy consumption by 87 joules, right? Which is absolutely a huge amount. And this is a really small change, okay? And when you're going from 100 joules of energy to 13 joules of energy, this 87% reduction in the energy requirement for the primary fuel means that you're extracting less crude oil, you're burning less crude oil, which means less fuel burnt and less CO2 emissions. Okay, so this is obviously one of the easiest ways of reducing the CO2 emissions. Just move to high energy efficiency devices, right? Now, so I mean, that's why energy efficiency is basically called the low-hanging fruit. It's the easiest thing to do, right? If you have a device which has high energy efficiency, please purchase it if it's affordable, if it's within your price range, because it always leads to lower energy consumption and lower carbon footprint, lower electricity bills, right? Everything is a win-win situation. Now, these are typical energy conversion devices with their efficiencies here, and you can see incandescent bulb sitting here, 10% efficiency, right? Not very high, which is why we have we have almost all of us have replaced the incandescent bulbs with an LED bulbs, right? So this is just one example, but there are several other devices in our homes which might be a bit old, which might be inefficient, and it's worth exploring if it makes sense to replace them with more efficient devices, which will surely be a win situation in terms of reducing your electricity bills, but the amount you save in your electricity bills may pay for the difference itself. Okay, so something worth doing the math for. Now, when we talk about energy efficiency and looking at picking devices with more energy efficiency, we also sometimes need to look at the overall efficiency in the picture, especially when the devices that we're talking about consume different energy sources. Okay. Now, we have seen in the previous example that every time you convert energy from one form to another, there is going to be a loss of energy, right? And if you have a system which requires multiple energy conversion processes, just like most systems require, we know that there is going to be an efficiency for each step, which means that you're going to lose energy at each step. And more steps you add, you're going to have more and more reduction in the energy input for the subsequent step, right? So if you talk about the efficiency of a multi-step conversion process, when we are looking at, let's say, the overall output, which is maybe of the process three, let's say that's what you ultimately care, and you take the energy input for process one, then the overall efficiency of the process, your desired output versus required input, would simply be a product of the efficiencies for process one, process two, and process three. So your overall efficiency would be efficiency of 3 to 1 times E naught, E naught being the initial energy input, right? And because this is such a strong function of the efficiency of different processes, so when you're trying to compare two different devices which take in different energy inputs, then you got to be careful in how you compare the efficiency, right? It may make no sense to compare something with an which is taking an energy input E2 versus another device that has energy input E0, because both have very different serial efficiencies, right? And you're not taking the serial efficiency for the second case. So whenever we are doing a comparison bit of energy efficiency, especially for devices with different energy carriers, let's say gasoline or electricity, we need to calculate the serial efficiency. If you're taking something that has the same energy carrier input, let's say gasoline, or for both devices, obviously just look at the system efficiency, the device efficiency. Like for the bulbs, we just saw, okay, the efficiency of the LED bulb versus efficiency of incandescent. Both of them had the exact same input. So you don't really have to bother. You look at device efficiency and you make your choice. But when you're looking at two different devices with different inputs, then you have to compute the serial efficiency. Okay, and I'll explain that with the help of an example. So let's say you want to compare which transportation makes more sense in terms of reducing your overall energy use and overall emissions. So let's say you want to compare a hybrid car versus an electric car. Okay, and you want to see which one would make sense if you were to buy one tomorrow. Now, when we're looking at the comparison of gasoline-powered vehicle, which is Toyota Prius, a hybrid vehicle, typical hybrid vehicle, versus an electric vehicle, the the simple answer might be, well, of course, the electric vehicle has to be better for the environment. It has to give lower emissions. But because these two devices, as they are, have different energy inputs, Prius takes in gasoline as an input, whereas Tesla takes electrical energy as an input. Uh, it is better to do the analysis in a more thorough manner, where you look into the overall efficiency of all the processes involved. Okay, so let's do that for Tesla. So let's say we're looking at Model 3 and you purchase a Model 3 because you think it's the best way to reduce the carbon emissions in your city, okay, or in your country. Now, if you're in Saudi Arabia, we know that the electricity is generated by burning fossil fuels, okay, and you're going to use that fossil fuel generated powered electricity to power your electric vehicle, right? Model 3 in this case. So let's look at the different energy conversion processes and their efficiencies at over the entire state. So starting from crude oil or natural gas extraction. Now this is very efficient in Saudi Arabia. The efficiencies are around 99%. Power generation, let's give some advantage to Model 3 and assume that you're making use of one of the new power plants and they have maybe a gas power plant and it has 40% efficiency, right? It can be 40, it can be 50. Let's take 40%, just as a reasonable estimate. Transmission and distribution losses, let's say they're rather small and the efficiency is 96%. Now, once the electrical energy reaches your home, then the conversion of electrical energy to mechanical energy in the Tesla motor, it's reasonably highly efficient. So we're talking about 85% efficiency. So now when you look at the amount of primary energy used, the overall efficiency from the input of primary energy to your ultimate output, which is just moving around in your car, you simply have to multiply all the efficiencies, just like we saw in the previous example. So the overall efficiency of the Tesla Model 3 in this case would be 0.99 multiplied by power generation efficiency, multiplied by transmission, multiplied by your efficiency of the car itself, 0.85, right? 85%. Comes out to be 32.3%. So uh, Tesla Model 3 is able to convert 32.3% of the initial primary energy available in crude oil into eventual mechanical work. And again, this number 32.3 has a lot to do with the efficiency of the power plant that you're using as well, right? If you increase the efficiency, the number will go up. So I'm not blaming Tesla here. I'm just showing a typical electric car and how it would be. The only thing Tesla can change is increase the energy conversion of the vehicle itself. Hopefully, they can increase it from 85 to 90%, which will be nice. But it is good as it is, and this is the number that we're dealing with. Now, let's do the same thing for Toyota Prius. Okay. Now, Prius takes in gasoline, right? So the process would look like, okay, crude oil extraction, then refining to gasoline. And once it's refined in a refinery, it needs to be transported to your retail station, your Aramco or Aldri's retail station that you go and get your fuel from, or Petromin or whatever. And then the eventual conversion of this energy available in gasoline, the chemical energy in the gasoline, to the mechanical energy to move the Prius around. When we look at the efficiencies, of course, crude oil efficiency we take the same. We're still in Saudi Arabia, 99%. Refining efficiency is rather high, 92%. There are no losses. There are very small losses in transportation and distribution. So we're taking 99%. And the conversion process from gasoline to mechanical work for a hybrid car is about 41%. So when we multiply all the efficiencies, the overall efficiency comes out to be 36.9%. Okay, which I mean, to be fair, is higher than what we had for the Tesla. Now, of course, these numbers would go up and down depending on the efficiency of the power plant, but the key point is to say that both are comparable, right? It is not as though Tesla Model 3 is an obvious winner if you want to decarbonize. In fact, if the power plant that you're taking electricity from has an efficiency of 40%, then your Tesla is actually causing more CO2 emissions than the Toyota Prius, right? So this is something that we see very clearly when we do a proper analysis, right? If you just look at it in terms of the device, you will say, okay, Tesla's efficiency is 85%, Prius is only 41%. There is no way it can compare. But in reality, their inputs are very, very different, right? And so a fair way to compare would be to look at the same input for both of them, and which is what we have done here. And it shows a more realistic answer, an actual answer of what is actually happening, irrespective of what maybe some of us want to believe. Now, I just want, so this was a very, very simple analysis, right? But I also want to show that this analysis did not give us some crazy numbers. These are very realistic numbers, right? And let's look at the well-to-wheel emissions for different passenger vehicles from IEA, okay? Now, this is the gram CO2 equivalent per kilometer, meaning how much CO2 will each car emit per kilometer driven. And this is for an internal combustion engine, hybrid, plug-in hybrid, battery electric, and fuel cell electric. Now, in reality, it's never going to be zero, right? They're just being optimistic because even if you use wind or nuclear, there are some emissions. There are some emissions of CO2, and you need when you generate some amount of electrical energy, right? CO2 emissions per kilowatt hour. But let's forget that for a minute. So when you see the range, right, the battery electric vehicle goes from a low of almost zero to a high of about 180, 190, right? And this variation is because it depends on how you're powering, how you're powering your vehicle. What is the source of electricity generation? If you're burning coal, well, of course, it's going to be on the higher side. If you're burning natural gas, might be slightly lower, right? But it also depends on the efficiency of the power plant. So depends on the fuel, depends on the efficiency, but it can be as high as this. When you look at the hybrid electric vehicle, you can say it's smaller than the worst case scenario for a battery electric vehicle. In fact, when you compare the averages, well, it kind of compares reasonably well. So there are situations where hybrid might be better. There are situations where battery electric might be better, right? But the point is they are comparable. It is not that a hybrid vehicle makes no sense at all. And therefore, considering that majority of the globe has electricity generation happening by burning fossil fuels, it makes sense actually to use hybrid vehicles as a way to decarbonize the passenger vehicles. They are an excellent short to medium term solution to decarbonize passenger vehicles. Right. So that's it for now. We'll continue more in the next class. Thank you.